Hey guys, Philip from Encode here. The lecture you're about to see is taken from Encode Academy course, so if you're looking for a broader context, you can find it at Encode Academy. But there shouldn't be any problem when you will watch it without watching the course, because it's very generic concept. So guys, I wish you nice watching, and I hope to see you in the lecture. Cheers! Okay, so how we are exactly storing numbers into integers on 32 bits. Okay, so as I was mentioning in the last lecture, get me my paper here. So we have here int32 structure. So integer stored on the 32 bits. So you have a 32, 1 and zeros. Okay, so you have a 32, 1 and zeros. Okay, so in a total you have a 32 of them. Okay, so how actually are storing the numbers, and especially how you are storing the negative values here? Because with the explanation I was actually explaining in a previous lecture, we were talking about only the positive numbers, but you can actually store also negative numbers here on the 32, in 32. To start from the very basics, first let's imagine all of this on the smaller amount of the bits, not on the 32 bits. That's quite a lot. Let's imagine everything now. Let's start explaining int 4. So everything stored on the 4 bits, and then we'll transit into int 32. Okay, so let's talk about integer of the length of the 4 bits. So everything can be stored only on the 4 bits. So for example, 1 0 0 0 4 bits, or 0 1 0 1, and so on and so on. Okay, so first let's see how many numbers we can store here in the int 4, okay? Even also with the negative numbers. Okay, so we know that the number 0 0 0 is storing the value 0, okay? That's definitely value 0. When we have a value 0 0 0 1, that's the value 1. Then we have a 0 0 1 and 0, this is the value 2. Then we have a 0 0 1 and the 1. All right, that's the value 3. So here is a 0 1 2 3. Then we have a number 4. Okay, so this will be 0 1 0 0. This is the number 4. Number 5 is 0 1 0 1. It's a number 5. And then we have a 0 1 1 0. That's the number 6. All right. And then we have a 0 1 1 1, and that's the number 7. And that's actually particularly, and I will be talking this in 32 in the C#, okay? In the C#. If you have using 4 bits, you can store only this many positive numbers. Because in a C#, even though when you have a 4 bits, the first bit here, this first bit here, is reserved for the sign of the number. So this 0 is saying that your number is positive, okay? So 0, the first bit, 0 is saying that the number is positive. Okay? So you cannot have a 1 1 1 1 1, because that will be already a negative number. So 0 1 1 1 means 7. First bit here, this is reserved for a sign of the number. This is saying this is a positive number. That's why we cannot store more values here for a positive values. Okay, and maybe a little bit recapitulation from the last lecture, how we are storing these values. So for example, if you have a value 0, let's say 0 1 1 1, how we are storing it. So basically, if we are starting from here from the right side, it will be 2 on the 0, 2 on the 1, 2 on the 2, and this one we are not counting because this is the sign bit, so that's a plus or minus. All right, so this will be 2 on the 0 is the value of the 1, 2 on the power of 1 is 2, 2 on the power of 2 is 4. So this is 4 plus 2 plus 1 is 7. Okay, that this bit is saying that it's 7. And the same when you have a bit, for example, 0 1 0 1, 0 1 0 1. So this bit is active and this bit is active. So this is the value of the 1. This third one is value of the 4. So 4 plus 1 is 5. So this would be in a base 10 system 5. And you can see it's matching here with our here 0, 1, 0, 0 is 4 actually. I would like to say 5. So 0, 1, 0, 5. 0, 1, 0, 1 is a 5. It's a 5 here. And 0, 1, 1, 1, 1 is 7 here. Okay, so that's how you're transforming this from the base 2 system to base 10 system. Each bit has a different value. You can see it here. It is a 1, 2, 4. If we would continue, if this wouldn't be signed bit, then we have a value. The next bit would have a value 8, then 16, then 32, then 64, and so on. As many bits we would have. Okay, but we are working only with 3 bits. Here, the first bit is for a sign. All right, so now we know how to store the positive numbers. How we are storing the negative numbers? Negative numbers in this system here will be stored as the negation of these values here. What I mean by negation, all bits will become, from the 0 will become 1, from the 1 it will become 0. Okay, so how we can negate 0, 0, 0, 4 zeros, we can negate them, so every bit becomes 1. So we have a value 1, 1, 1. From these 4 bits, when we'll negate this, we'll get here 1, 1, 1, 0. So 1, 1, 1, 0. Here 1, 1, 0, 1. So 1, 1, 0, 1. Here we have a 0, 0, 1, 1. So this is the 1, 1, 0, 0. Here you have a 0, 1, 1, 1. So 0, 1, 1, 1. Here we have a 0, 1, 0, 1, 0. And here we have a 1, 0, 0, 1. You can see I'm just flipping the values. And here we have value 0, 1, and 0, 0, and 0. Okay, and now again, as before, actually, when you're working with the positive numbers, the first value, the first bit is saying the sign of the number, so 0 saying that it's a plus. But in the case you're working with the negative numbers, if the value is a 1 here, the value is actually negative value of the 1. I will show it to an example, okay? So this value would mean this is the -1, here is -2, here is -3, and here is the -4, here is the -5, here is -6, here is -7, and here is a -8. You can see the negative numbers we can actually store from the -1 to -8, positive numbers from the 0 to the 7. Here our computations are working when we are working with the only 3 bits. First bit is a sign bit, which is saying the sign of the number. But here, if you will try to transform this here, you will not get the right values. Okay, so when the first bit is a sign bit, actually this is called signed magnitude. So this method is called signed magnitude. Signed magnitude. It's very hard to write with the mouse, actually. Oops, and somehow I lost it. So magnitude. All right, it was very hard. All right, so signed magnitude. So on the positive numbers, we are using signed magnitude method, where the first bit represents the sign of the plus, and all of the 3 bits represent the actual value. In the negative numbers, it's slightly different. In the negative numbers, this is called to complement. Okay, this method is called to complement. I hope I will write it, to complement. Complement. Where the first value, actually, here is 1, represents the value as it would normally be as a positive one, but it's negative. Okay, so when you have a number 1, 1, 1, 1, as we saw it before, this is the value 2 on the 0, this is the value 2 on the 1, this is the value on the 2 of the 2, and this value on the 2 on the 3. Okay, so this means this value is the value 1, 2, 4, and this is the value 8. But in the 2 complement, this will not value 8 when you're working on the 4 bits, but this will be negative 8. So first number will be representing negative 8. All right, and suddenly it starts making sense. So number 1111 represents minus 8 plus 4 plus 2 plus 1. So this is 4 plus 2 is 6 plus 1 is 7. 7 minus 8 is minus 8 plus 7 is minus 1. Right? That's correct. Here again, here you have 3 ones and 1 0. This means minus 8 plus 4 is minus 4 plus 2 is the minus 2. Okay, so that's a minus 2 here. And so on. If you have a 1 0 0 0, this means minus 8. Yeah, makes sense. If you have a value 1 0 0 1, this means minus 7. Yeah, it makes sense. First value is minus 8 and the last one is 1. So minus 8 plus 1 is a minus 7. So everything is fitting together. So if you are working with the 4 bits, the first value in the case of a positive numbers is the method is called signed magnitude. First number represent sign, so 0 represents plus. So you're working only basically with three bits. So just 3 bits represents the magnitude. The first bit represents the sign, okay? And in the case of negative numbers, when you have first 1 number, when the bit starting with a 1 and you're working with the 4 bits, first value represents its negative value as it would be normally. So in this case, minus 8 in the case when we are working with the 4 bits. Okay, and actually we can translate it to any representation of the bits. So if you're working with the int 4, we can same work with the int like this with the int32. But in this case, everything will be represented on the 32 bits. Instead of the 4 bits, you will have a 32 bits. If you're representing the positive number, the first number will be 0, and 31 numbers will represent its magnitude. If you're working with the 2 complements, first one will represent the huge negative value, and other numbers and other bits will represent its positive value. You can actually see it in the description of the C# of the int32 in the int32 structure. Okay, I'll show it to you. Okay, so I'll hide this for a second. I'll go to browser. Okay, that's from the other lecture. I will look here from the C# int32. All right. Okay, I would like to have here English. That would be better. Let's see if we find here English. So int32. Okay, and you need to scroll on the bottom of here. And here is a small description of working with the non-decimal 32-bit integer values. All right, so let me see here. So positive values are represented by using signed and magnitude representation. That's what I wrote here. Positive values are represented by using signed and magnitude representation. Negative values are in 2 complement representation. So in a case of a 32 bits, the maximum value you can get here is actually this value here, huge value. This maximum positive value on the int32 can be 2,147,483,647. That's a maximum positive number. Negative value here, maximum negative value here is a negative, almost even number, 2,147,483,648. You can see the negative number represent more values here, as the same as we worked with the 4 bits. Here the positive could be only 7, but negative can be represented as minus 8. The same thing is with the 32 bits. You have here this value, and this is here. This is negative value, and here is a positive value. And that's basically, guys, how it works. So I think we still have a time for a little small experiment. We can experiment with this with these values. We can place them into code. We can console a couple informations. Okay, so let's do it. But I think I will use here some online console. Okay, so let's open browsers and let's search here for C# online compiler or something. Let's C# online.net fiddle. Okay, that's fine. Here we can write code, we'll run it, and this will execute the code. You can see it here, hello world. But instead of the hello world, we'll be executing here a transforming function. So let's write here. So let's say var num, let's say number 5. I would like to transform it into the binary. So I'll write here console write line. All right. Okay, I think this will be more visible like this. Okay, write line. And I will write here some message. Let's say number plus space is in binary colon space plus now method convert to string, and we are converting our number to the binary like this. Okay, so what is a 5 in binary? Plus 5. Plus 5 in a binary should be 0, 1, 0, 1. Okay, so let's see. So let's run this. And we are missing here something. All right, compilation error, identifier expected. Let me see, console write line num plus space is in a binary plus convert to string. And I think I have here too many brackets here, so this bracket shouldn't be here, and this bracket shouldn't be here, like this. Okay, so let's run it now. And you can see 1, 0, 1. That's exactly number 5, as you can see it here. 1, 0, 1. Again, first bit is used for a sign, and in a console log it's omitted. It's not simply not written here, but if you would work with the 32 bits number, there would be another 28 zeros in front of this number, but you are simply omitting them. The number 5 represents 0, 1, 0. All right, that's basically it. So if you, for example, number 6, okay, you can test it out. Number 6, run this. This is number 001. Okay, number how do you say 7? Number 7 should be all the bits active. Okay, that's a binary 001. Again, if you would work here, I think I will remove it, guys. Okay, so if you would work here with the 4 bits, the first bit will be 0. All right, but you simply don't need to write it in a console log, because that's already, this information is not needed, because you just need to provide the bits that provides the value of these 4 bits, and the first bit is always just a sign, so you can omit this. All right, and in a case if you would work here with the 32 bits numbers, then you would have here in the front another, I don't know, 28 bits, right? So another 28 bits would be in the front, so 28 zeros in the front. But simply, again, you don't need to write them. You can just provide the actual, what represents your value of this. Okay, but that's not the case when you're working with the negative numbers, because when you're working with the negative numbers, let's write here -7, it will display all of the bits here. So now you should have here display 32 bits, because you need all of the bits to represent the negative number. Let's count it here together. Okay, so this is the first bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 28, 29, 30, 31, 32 bits, because first bit represents this super huge number, super huge minus number, and all these bits represents the positive numbers. So if you would like to display the maximum number minus value, so this value here minus this number here. All right, so this number here, we need to remove these commas here to billions. All right, let's run this. This would be this number here. So that's the maximum number. This number here, when you have just the 1 and 31 zeros, this represents this minus 2 billions, 147 millions, and so on. Okay, so that's the maximum number minus value you can get in the representation of the 32 bits integer. And you can see that we are working with a 32 bits integer. When I will console log here, console write line. All right, so let's write me here the number. Okay, so I will get here number and the get type like this. Okay, let's run this. You will see we are working here with the int32. So integer representation on the 32 bits. All right, and that's basically it. So when you have a negative numbers, we need all the 32 bits to represent the negative number, because the first bit represents this value minus 2 billions, and this value you can see here. In the case of the positive numbers, we don't need this. This is a maximum positive value. Let's run it. 31. This you have a 31 ones, and you can omit the first 0 because that's you don't need this information. It will be 0 here, and 0 says that it is a plus number. And here I have a 31 of the ones. That's a maximum positive number you can get. Okay, I think it's pretty clear right now, but we can also go other way around. So let me write here. Let's write here binary number. Okay, so let's write here var binary, and let's get here's number. Let's say 111. All right. Okay, again, we are working with the 32 bits. So var here, we can write here explicitly integer binary. 11. Oh, it's gonna be integer. This is a string, of course. 111. All right, and we can transform it into the into base 10 system like this. So let's write here. Let's copy this line here. All right, to format it correctly. So console write line here. Let's write here binary. Let's write here is in base 10 system, and here we'll use a different method. So we will convert it to integer 32. Okay, so to integer 32, we'll get here our binary number. So binary here like this, and let's see it. So let's say we are converting this 111. Guess the value is the value 7. So 111 in a base 10 7 is in base 10 is a 7. And I told you I don't need to say here this is 0 here, because that would be already implicit information here, because that's the bit that's saying that this number is just a positive. So if I would run it, it's still 7. 0, 111 is still 7. And if I would write here, because 32 bits in 32 is represented on the 32 bits, if I would write here, it's 28 zeros. So 1, 2, 3, 4, 5, 6. I hope I have 6 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So now I have here in total 32 bits. This would be just still 7. All right. So I can freely, if I'm working with 32 bits, I can omit this information. That's these informations I really don't need, because I can just say this, and this represents number 7. All right, but when I will represent here, let's say bigger number, I need to write here, of course, 1. Okay, this represents the value of this, for example. Okay, but when I will already write here 1 here, this value is this. Okay, how many bits I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I have 31 bits here. So we will write here one more 1. It should be negative number. Yeah. Okay, now I have a 32 bits here. But when I will say here this first 0, this will be positive number. Yeah, that's a positive number. But if I would say here this first one here, this is already negative number. So it doesn't matter. I will change here 1 and zeros. It will be always now negative number, because the first number is this 2 billions and something, and all of these are positives. All right, I can change it here like this. It will be positive number. All right, I can change it back to the zeros like this. This will be this number here, 13,000 something, or 131,000. And I told you I don't need these informations here, because this is the same as writing it if it's zeros, and it's again the same number. Okay, guys, I hope now it's clear what we are talking here, and I'm explaining here this int32 structure. So two complements method and signed magnitude in the case of a C#. How does it work? This is how it works, but in a different programming languages, it can work. It can work differently. So keep this in mind. But you can already see here patterns, and you can already think about this by yourselves, and you can learn the other methods very easily. So, guys, that should be it from these lectures. If you have any questions, just feel free to ask them. And yeah, I hope to see you in some of my other lectures. So guys, that should be it. And yeah, see you in the next one. Cheers.